All right, so if you're deep into your circuits class right now, you've probably got Ohm's law and those resistor color codes practically tattooed on your brain. But there's another number lurking on that spec sheet. It's just as critical as the resistance value, maybe even more so, and if you ignore it, well, things can get a little smoky. Yeah, we're talking about the power rating.
So you've seen it, right? On a parts list, it'll say quarter watt or half watt. But what does that really mean? Let me tell you, it's not a friendly suggestion. Nope, it's a hard physical limit. And getting a handle on this is the difference between designing a circuit that works like a charm and one that, literally goes up in smoke.
Okay, so let's start with the first big clue. And it's something you've probably felt yourself if you've ever touched a circuit that's been running for a bit. Resistors, they get hot. And that heat, that's not a bug, it's a feature. That's the resistor doing exactly what it's designed to do: convert energy. You can kind of think of it like friction, right? As all those electrons get shoved through the resistive material, they're constantly bumping into atoms, creating all this microscopic chaos. And what does that chaos generate? Heat. So at its core, a resistor is just a little machine for taking electrical energy out of your circuit and turning it into thermal energy, heat, that just radiates away. So just remember that. Every single time current flows through one of these little guys, there's a real physical transformation going on. That resistor on your breadboard isn't just some abstract number in an equation. Nope, it's a tiny, purposeful little heater, actively turning electricity into heat. Okay, so this whole energy conversion thing, it doesn't happen for free. In any circuit, there's a price to pay for doing work. For a resistor, we measure that price as a voltage drop. And this is the absolute key thing to get. That voltage drop you measure with your multimeter, it's the direct result of that energy being turned into heat. It's literally the electrical price you pay to shove current through that resistance. No energy conversion, no voltage drop. Simple as that. So, if the resistor's job is to make heat, our job as engineers is to figure out, okay, but how much heat? We've got to put a number on it. We need to quantify the rate of that energy conversion. And that, my friends, is where electrical power, measured in watts, comes into play. The most fundamental formula is beautifully simple. Power equals voltage times current. P equals V times I. This equation tells you exactly how fast that resistor is pumping out heat. It's the rate in joules per second, which is just another name for watts, that electrical energy is being converted.
Okay, now here's a version you're probably going to use all the time. Power equals current squared times resistance. P equals I squared R. This one is super handy because a lot of the time you know exactly how much current you're dealing with. But you have to pay attention to that squared term. It is a huge deal. It means if you double the current, you don't just double the heat, you quadruple it. That's a game changer.
And for the trifecta, we have power equals voltage squared divided by resistance. P equals V squared over R. Look, the main thing to remember is that all three of these, P equals VI, P equals I squared R, and P equals V squared over R, are just different flavors of the same thing. They're all just Ohm's law mixed around a bit. You just pick the tool that fits the job, depending on which values you have handy.
All right, so you've crunched the numbers. You used one of those formulas, and you figured out your resistor is going to be spitting out, say, 0.2 watts of power. So, now what? Now you have to leave the world of paper and pick an actual physical component that can take the heat.
I want you to think of a resistor's watt rating like a speed limit, but for heat. It's a thermal speed limit. It has nothing to do with how much heat the resistor creates. You calculated that. It's all about how much heat it can safely get rid of before it literally cooks itself to death. And that limit is all about its physical construction, its size, its materials. A bigger resistor is like a bigger radiator. It can just shed heat more effectively. So the process here is really straightforward, but you absolutely cannot skip it. Step 1, calculate the real power your resistor is going to dissipate. Use I squared R, whatever works. Step 2, look up the standard power ratings that you can actually buy. You know, an 1/8 watt, a 1/4 watt, half watt, all those. And step 3, and this is the golden rule, you have to pick a resistor with a rating that is higher than the number you calculated.
Let's make this super practical. Imagine your calculation says your resistor will be dissipating 0.2 watts. Okay, you look at your parts bin, you see a 1/8 watt resistor, that's 0.125 watts. Is that enough? No way, that thing will get toasty and fail. So you look for the next standard size up. A 1/4 watt resistor, that's 0.25 watts. Perfect. It's above your calculated value, it gives you a little breathing room, that's your safe choice. And listen, picking a resistor that can handle the power, This isn't just about being a good student or making your circuit work for the lab report. This is a fundamental safety issue, and it becomes way, way more important as you move on to circuits with more juice flowing through them.
In fact, here's a really solid rule of thumb from the pros. Design with a big safety margin. Don't just pick the next one up. A good target is to pick a rating that's at least 50% higher than what you calculated. So, for that 0.2 watt example, a 50% margin means you'd want a resistor rated for at least 0.3 watts. That quarter watt one is okay, but the smarter choice is to step up to a half watt resistor. Why? Because that extra margin means it runs cooler, and a cooler component is a happier component that will last a lot longer.
Let me be crystal clear about this. When you force a resistor to handle more power than it's rated for, it will get dangerously hot. I'm talking hot enough to desolder itself right off the board, hot enough to scorch your PCB and kill the components next to it. And in a worst-case scenario, yes, it can absolutely catch fire. This isn't some textbook warning, this is a real thing that can happen in the lab.
All right, let's wrap this up. What are the big takeaways? First, resistors are basically just tiny heaters, converting electrical energy into thermal energy. Second, power, measured in watts, is how we measure the rate of that conversion. Third, you must calculate the power dissipation for every single resistor. And fourth, always choose a power rating with a healthy safety margin. Seriously, heat is the #1 enemy of all things electronic. Don't ever underestimate it. So as you move forward in your classes, I want you to think about this. The equations you're learning are perfect, idealized models. But the real world, the world you'll be building in, is all about physical limits. The power rating of a resistor is one. The breakdown voltage of a capacitor is another. The maximum current of a transistor, you get the idea. Learning to see and respect these invisible limits, well, that's what turns a student into an engineer.